Hello, this is the second lecture on Introduction to Remote Sensing. As you can see that now we are going to discuss in this particular topic the development of remote sensing technology and advantages. So, we will look some history and we will see that why remote sensing is so useful. That means the advantages. There are various advantages of remote sensing over conventional techniques, and we will see all those details. As mentioned in the previous lecture, that is the Introduction to Remote Sensing first lecture, that the current remote sensing is did not develop in just one day. It took centuries basically. As you can see that the first time the aerial photographs was taken from a hot air balloon in 1858 as a drawing is shown here, and the photo luckily these have been preserved. So, these the photographs of through that camera which we have taken are also shown here. So, basically that was also a remote sensing which brought us to this current day remote sensing. So, it is basically, if you look the history of remote sensing and the development, the development journey of remote sensing, basically we can put in 1858. And of course, later on in World War II especially, there are a lot of extensive use of remote sensing was done. But before that also that words were also used to put their the cameras and then flown over it. So, in 1903 this kind of experiment was done. Later on that plane mounted cameras were also used in 1945 when this World War II was going on. And then in 1947 the first space based photo taken on 7th March 1947, and this photograph is shown like this. But these were not scanners, these were not imaging systems, these were the cameras and we took the snapshot. There is a large difference between these snapshots and a scanning, which we will see in later lectures. So, this was taken by an automatic camera K12 using black and white infrared film and from Viking sounding rocket that reached a height of 227 kilometers. Nowadays these polar orbiting, earth orbiting satellites are orbiting around 800 and plus 850 plus minus a few kilometers they are orbiting. So, much deeper in space the current day remote sensing is being done. But anyway, this is how things developed. First through balloons, and then space borne or space based photo taken, and this is a New Mexico, Arizona, Nevada, California and New West Mexico was captured in 1947. In 1961 the earth this was taken by a satellite which is Mercury Redstone 3 spacecraft on 5th May 1961, and which was the first US manned space flight. So, this was a man in this space flight, the man was there and or astronaut was there, and it has taken the photograph. Later on other missions also, like Apollo lunar landing missions also, the photographs not only of the earth were taken but also of the moon. The real remote sensing, the boom in remote sensing really started since 1972 after the first launch of this series of satellites, and the first one in that series was Landsat. Earlier, if you open some older books, you would find that the name of this satellite was ERTS, Earth Resources Technology Satellite. Later on it was renamed as Landsat. So, we started the real operational to the current remote sensing since 1972, and the good part is that the most of the data which these satellites, the series of Landsats have recorded, are now available for us to use. So, more than 45 years of now, roughly 45 years of the data is available, and therefore people are employing these data sets for long term studies especially in climate change or in environmental related studies. So that is the biggest advantage, that the archives since 1972, after the Landsat 1, which was launched on 23rd July, are now available almost free of cost for utilization for different applications. Then another boost came because the Landsat 1 was giving the data. It has the sensor, which is the multispectral scanner, MSS, and it has a resolution of 79 or roughly we say 80 meter. Now this was improved, this spatial resolution was improved, much improved spatial resolution through this spot, which was a French Earth orbiting satellite in 1986, and it had the new sensors, very high resolution relatively at that time, very really high resolution. That means it started providing data at 10 meter, that was the panchromatic, that means black and white, and also 20 meter, that is this multispectral data through this spot. So that brought a major jump from a spatial resolution from roughly 80 meter to 10 meter and 20 meter. That was a great boost to remote sensing through this program of French Earth observation satellite, that is SPOT in 1986. Nowadays many countries, more than 12 countries are having their own satellites, including India, including China, Japan, and even Dubai, which is UAE. Dubai is a city of UAE, which is not a very big in that sense, but they too are having their own satellite. So now many countries are having satellite, and that is why the earth is enveloped by many types of satellites. Many of them are working, and some of them have lived their lives or have become defunct, and though they are present in space. So in 1970-80, the rapid advances in digital image processing parallelly also developed, and that also basically brought impetus in the remote sensing technology, because the data started coming, lot of data started coming from various satellites, and the same time good digital image processing tools, especially software tools, were developed so that people can utilize, analyze the data, make good interpretation and excellent applications. In 1980s, the development of hyperspectral sensors. Like in Landsat MSS, there were only 4 bands. People started looking more thinner bands, means narrow bands, and also many bands, and that basically brought the development of hyperspectral sensors. So earlier these sensors were initially they were flown on aircraft, tested, and then later on they were put on the satellite. Like one of the example of Aberis, which was developed by NASA, and they had many channels, not 4 channels, 10 channels or 36 channels like in MODIS, but they had now like 200 channels, 155 channels or 255 channels. So for a very micrometer thick bands made available. So that is another large development which has taken place in remote sensing. Now there are satellites also in hyperspectral range as well. Then in 1990s this global remote sensing system started coming. That means we developed the better communications, so we can cover any part of the earth any time, and that kind of thing. If we look the development of remote sensing in India, so it started basically in 1975 when we had our first satellite launched, that was named as Aryabhat, and later on then we had the Bhaskara 1, Bhaskara 2, and they had some cameras visible, near infrared camera, and also some microwave radiometers also at that time. Later on the real as in case of world remote sensing, the Landsat became the landmark development. So in case of Indian remote sensing, the IRS series became the landmark. And basically it started in 1988, in March 1988, the IRS-1A satellite which was launched. We will go through a list of Indian satellites and foreign satellites, how in the history we can put them in a chronological order, that the IRS system is the largest constellation of remote sensing satellite for civilian use in operation today in the world, with the 12 operational satellites. So now we are left that series IRS 1A, 1B, 1C, 1D after that. Then we are having Cartosat, ResourceSat. Very recently Cartosat 2 has also been launched. And then this program of Indian remote sensing program continues, and even we are launching these satellites. Only roughly 3 years back we have also completed 25 years of our successful remote sensing operations in space. So this put in perspective the Landsat program, as I mentioned earlier, that is started in 1972. 1st July 1972, and it lived a quite long life, about more than 5 years, though generally these type of satellites are designed for mainly 3 years, but if design part is good, launch is good, then they may live even for 10 years. So this was very successful mission. Then Landsat 2 came, Landsat 3 came, 4, 5. 6 was very short lived satellite, somehow there were some technological problems, and then 7 and 8 too has become very successful, and this is for the future, which we will see very soon. The other important thing is, which you should be able to notice, is that there are overlapping all the time, that it is not that whichever the country which are having long term remote sensing programs, they always go for overlap. And so in India, but like if we are looking the Landsat case, that see there's roughly in the half time another satellite was launched. So for a few years we had 2 satellites together in tandem in space of Landsat series. Then when Landsat finished, then Landsat 2 and 3 were there in space. There was some less overlap was there, then a very longer overlap. And similarly in case of our IRS series and other, we also had this kind of overlap. So what it provides, that there is a continuity of the coverage by our own satellites or by a particular series of satellites. And secondly, that the repeativity means suppose once the repeativity, or we call as a temporal resolution, is revisit time. Suppose a satellite is having revisit time of 16 days. Now if you are having 2 satellites in tandem, maybe for whatever the time period we are having, and if they are designed or put in space in a manner that after every 8 days you will have one scene of the same part of the earth. So this is the advantage of having overlapping satellites in tandem. Here is our ISRO mission, and we are only looking after this IRS, that is March 1988 onward of earlier we were using, as you might be knowing, that some foreign vehicles, launching vehicles, and but then with the IRS 1D we started with our own PSLV series of our launching vehicles, and since then we have been not only launching our own satellites, but foreign satellites of different countries, even US, Russia and France and many other countries. Satellites are now being launched by the launching vehicles, which is a PSLV. So IRS 1A and this series continued, P4, P5, P6, then Cartosat 2, then OceanSat, Cartosat 2B, and ResourceSat, RISAT. This is a different satellite, this is radar remote sensing satellite, but that too have been launched in 2012. So many of them are still in service, some have completed their missions, and so on and so forth. This is because each satellite has got some design life, many of them live more than design life, many because of some other reasons may not live even their design life, but that is very rare thing. Now this thing between the remote sensing which is available to us through sensors, means imaging devices, scanners, and the other side of the data is available through aerial way. So we will see the difference point by point, that what is the basically difference between the normal remote sensing or aerial photography, which was a technology lasted for many years, was quite useful. So what we see is that the current satellite remote sensing is having very high speed, high temporal resolutions, like it depending on the spatial resolution. If it is having relatively coarser spatial resolution, it can provide the data of the same part of the earth even 2 times or 4 times in a day. For example, NOAA AVHRR data, and there are satellites which can provide data even after 35 days, like radar remote sensing data. So depending on their orbits and the resolutions, this thing is there. But for in case of aerial photography, it is slow. It has to be put in has to go in the air and then take the photographs of a small part of the area, whereas satellites keep scanning different parts of the earth continuously, daytime and night time, if they are having thermal sensors. So that is the biggest advantage with it's a regular thing, and we can say aerial photography is not regular. Once the satellite is launched, and if it becomes operational, then regularly it is scanning the part of the earth, whereas it is not true in case of aerial photograph. And levels of details nowadays, like GeoEye satellite, we can have even 50 centimeter spatial resolution data, which may not be possible with this. Sometimes with aerial photographs, with low flying aerial photographs, we can have 2.5 centimeter, but this is very rare and very expensive as well. Weather conditions, cloud is a big hindrance in optical data, especially with the satellite data. So this is a sort of negative in case of present day remote sensing, but in case of aerial photograph you can avoid. If you know there are clouds, the area which you are going to cover, you will not fly the aircraft, so that can be avoided. Then type of data, the less as each new data type needs new satellite launching. So type of data is also available, wide variety of data is available from satellite, whereas the type of data high as new data types needs sensors to be mounted in aircraft. Location, now that is another advantage. As I mentioned that the big impetus came in remote sensing in World War II. So the territory, across the territory people wanted to have the information, and therefore at that time the aerial photography started, and looking obliquely in the other side across the border. So location, cross border images and large swath images can easily be taken by the satellites which are doing regularly, and the location here, cross border images cannot be taken without permission generally, but in case of war or some emergency situations these things are being done. Now post processing is required in case of satellite data, but because of huge development in digital image processing and very advanced some semi-automatic or automatic image processing tools are available, which makes us to process large amount of data which is being acquired by the satellites. And then post processing it is tough, though due to large numbers of images covering a small area, because the aerial photographs these are having a fixed size and they becomes in very large number, their mosaicing, their processing becomes very difficult, because they suffer from lot of distortions because of the movement of the these aerial photographs. So this brings the basically the major differences between satellite remote sensing and aerial photography. Now this current day remote sensing can be divided in 2 major parts basically. One is active remote sensing and another one is passive remote sensing. Passive remote sensing is very popular, active remote sensing is having limitations, but nowadays it is becoming popular, and especially with the development of this SAR interferometry. And many countries are now having their own satellites or planning to have their satellites in active remote sensing. But there are only few satellites in space in this domain, whereas the passive remote sensing is much easier and lot of satellites are there. Even in passive microwave regions, there were some experiments were also done. So passive provides a lot of remote sensing data. So because passive doesn't employ any external source of energy, and whereas in case of active remote sensing has its own source of energy. What does it mean? Basically it means that because for passive remote sensing, either you are having solar radiation, reflective radiation, which is available to the sensors which can record the different objects of the earth, especially in daytime, or emitted energy can also be recorded, maybe in microwave region as well. So for that you do not require any external source of energy. Whereas here in case of active remote sensing, the satellite or the sensor itself has to send some signals, energy, and then that is attenuated, reflected back, and then collected later. So that is why it is less common, but it is becoming very powerful tool of remote sensing, that is active remote sensing, especially SAR interferometry, which we will see little later. Now the what passive remote sensing is doing, as mentioned earlier, that measures either reflected radiation from the sun, can be operated only during daytime, or the emitted radiation from the surface day and night time. So if you are having thermal sensors, you can record the data even in night time, like in case of Landsat, after Landsat 4 till Landsat 8, all these are having thermal sensors, and therefore even in night time you can record the emitted energy through these thermal channels. Same with the NOAA AVHRR data. So AVHRR sensor on board of these NOAA satellites are also having two channels in thermal band, and therefore we can also record the data in night time as well, though they are also having visible and near infrared and infrared channels as well. So that is the advantage of having this kind of passive remote sensing. Active sensors emits a controlled beam of energy to the surface of the earth, and then whatever is reflected back, it is recorded, and this is how these images of microwave, basically microwave remote sensing images are formed. Then passive remote sensing suffers from variable illumination conditions of the sun, because you know that the sun having the varied illuminations depending on the season, because of clouds and so on. So that might create some problem in our passive remote sensing, and may influence the atmospheric conditions as well, that we have also discussed a little earlier. We will see in much detail what are the atmospheric distortions and how these quickly can be corrected in some cases. And here what we are having, because the satellite or sensor itself is sending the energy, and therefore it is controlled illumination signal. So that question of atmosphere and other things will not come, because here the wavelength is larger, and then that atmosphere present between sensor and the earth does not create much problem here. These operations in active remote sensing can be done daytime or night time. There is hardly any difference, because the source of energy is from satellite itself, sensor itself. Then what are the advantages? This is the point basically which brings the usage of remote sensing, or why it has become very popular in the last 30-40 years. First of all, it provides the synoptic view. What does it mean? Synoptic view means here that when it is satellite is orbiting, it may cover a very large part of the earth. And another very important thing, which that point might come later in the slides, is that it records the unbiased in an unbiased manner. So whatever the recording which is available, there is no human interventions, directly the sensors is recording. So it provides a unbiased recording and a synoptic view. A large part is covered by these. And another advantage is it is a global coverage. Most of the satellites, these satellites are covering entire globe, though somebody might not be recording the data, or somebody may not be having the earth stations in different countries of all satellites, but the satellite itself might be transmitting the data or directly broadcasting the data towards the earth and covering the different parts of the or all parts of the earth. So that is the another very good advantage with remote sensing, global coverage, repeatability. It keeps covering the same part of the earth and depending on the resolution and the orbit. So some satellites, as I mentioned, that like NOAA AVHRR sensor, they can cover even 4 times in a day, 2 times in daytime, 2 times in night time, whereas some satellites may come after 12 days, 16 days, 18 days, depending on their resolution, swath, width, and so other thing. Now multispectral sensors can, another advantage with remote sensing, that not only you are recording in panchromatic, but you are also doing in multispectral sensors. So that can also be can be recorded wavelength beyond range of human vision, as mentioned in the first lecture, that our eyes are only sensitive in visible part of the earth, whereas the sensors we can design which can sense the earth or scan the earth not only in visible part but near infrared, thermal infrared, even in passive microwave regions. So multispectral sensors are available through remote sensing, which is otherwise not possible. Multi-resolutions data, even on one same satellite, we can have different sensors having different resolutions. Example came about spot. So it has panchromatic camera, 10-meter resolution, it has 20-meter resolution, multispectral data. Same example started coming with our own IRS satellites. We had once this panchromatic camera at 5.8 meter resolution, and then we had the list 3 sensors like 23, 5.5 meter resolution. So same satellite can have different sensors of different resolutions. So that is another advantage. For the same date, you are having different resolution data from the same satellite. So that the atmospheric conditions are constant throughout these sensors. Near real time it is possible because when the satellite is overpassing, generally these are also directly broadcasting or transmitting data towards the earth. If these data is not incorrupted, one can even have their own satellite earth station, like in IIT Roorkee in Department of Earth Science. Since 2002 we are operating NOAA AVHRR earth station, because NOAA is directly broadcasting. So we don't have to have a license or encrypting code or any other thing. We can just record the data whenever the satellite is overpassing our earth station. So in near real time the data is coming. That is another advantage, especially in disaster related applications, that provides the very big advantage. Systematic data collection, because the orbits are fixed, when the satellite will come we know in advance, even 7 days, 8 days before we know then when satellite will overpassing a particular part of the earth. So lot of things can be designed accordingly, lot of missions can be designed, and therefore the data collection is very systematic through remote sensing. And this is the only solution sometimes for otherwise inaccessible areas, especially like in high mountain terrains like Himalaya, very highly rugged, all parts cannot be reached very easily by the humans or by other means, but remote sensing can reach. So that is the very big advantage. Same thing also happens in case of any natural or man-made disasters, that the first thing people start looking remote sensing, because it can acquire the data. There might be some satellite at that time might be flying over that part of the earth where a natural disaster has occurred, and therefore you can get that data and analyze and can see how things developed or how this has happened. And one very important point which I mentioned about these 3 technologies, that is remote sensing, GIS and GPS, that these are the generic technologies, and therefore their applications are many, several, and some still we don't know. People are developing. So the remote sensing data is generic, and therefore it has got multi-purpose applications. So it can be applied for various things, from climate change to natural disaster to civil engineering to mineral exploration to oil exploration, whatever, wherever one can think, can nowadays can apply. Meteorological applications are there, and for weather forecasting it is now extensively being used, these technologies, in integrated manner. And of course it is cost effective, because once the satellite is launched, it may last, may live for 5 years, 6 years, sometimes they live for even 10 years and keep providing data continuously. And therefore the initial cost is much more, and later on only the some operational cost, recording of the data, making archive, and of course analysis, interpretations, those things are there. But even then, overall if you see, it is highly cost effective technology compared to other conventional methods, especially ground surveys and other things. So this brings this in a large perspective. We can see that the remote sensing is unobtrusive. If the sensor passively record the EMR, that is electromagnetic radiation reflected or emitted by the object of interest, passive remote sensing does not disturb the object or area of interest. So whatever is being done, it untouched by any sensor. And the remote sensing devices may be programmed to collect data systematically, such as within a 10 kilometer by 10 kilometer frame or vertical aerial photography. This systematic data collection can remove the sampling bias introduced in some of the, because this term I have used, the remote sensing provides completely unbiased recordings of the any event which is happening on the earth, anything which is happening on the earth. For example, there might be forest fire, for example there might be earthquake and ground deformation, associated ground deformation, and might be flooding and so on and so forth. So this is completely unbiased recording is also available. Under control condition, remote sensing can provide fundamental biophysical information, including location, elevation, depth, biomass, temperature, moisture content. Because if we integrate the GPS, then we get the location. If we integrate or put on GIS platform, we can extract few more things. The temperature is being driven from remote sensing through these thermal sensors, and there are different algorithms by which we can estimate the temperature of the earth, or even sea surface temperature, or a temperature over a volcano, temperature over a forest fire or coal mine fires. Those things can also be done. And of course moisture content and other things, people have developed applications not only in this infrared or other parts, but also in microwave remote sensing. So this brings to the end of the second lecture on introduction to remote sensing. Thank you very much.